This video we're going to be tackling this definite integral, which is the integral from 0 to infinity of sine of x divided by x dx. I'm not sure whether or not it started in this family or whether or not there was a family that was made out of this, but this is actually part of a family, a really famous family of integrals called the Born integrals. If we have a look, I may have Born integrals, sorry, and there's some remarkable properties that exist within that that we can talk about later on. Nevertheless, this is an integral that, using conventional substitution techniques, at least to my understanding, there is no actual way of being able to evaluate it. However, and as what we have titled here, there is a method that was introduced by Richard Feynman known as Feynman's trick that is incredibly useful in taking a definite integral and transforming it into a integral transformation style situation or an integral function, and then using some sort of operator, so in this case we're going to be using differentiation in order to be able to evaluate it. Now, I've only been actually doing this for about a year, and it's just completely revolutionized how I look at integrals. There is no predefined method when it comes to Feynman's method, if you will, and that's probably why it's not called Feynman's method. Sorry, I shouldn't have called it that. It's called Feynman's trick. You essentially work at trying to find a way of transforming the integrand in some way in order to allow for the integral to be evaluated under some operator, differentiation. It could be a Fourier transform, a Laplace transform, a Mellon transform, or whatever you want, and then evaluating it and then taking the inverse of that operator in order to be able to resolve it. So there is actually some heavy calculus theorems that goes into this. Or should I say into the application of it. I'm not going to go into a great detail yet. At the beginning, I just sort of want to illustrate a few examples of it to get people interested and motivated, and then from there we can go into, I will do, if people actually want to let me know within the comments, a follow-up video that will go into some of the theorems that are required in order for this to actually work. Okay, so the big issue generally that we see within here is that we've got this division by x, and so that really is causing a problem. So we need to think of something, and in this case it's going to be within differentiation, that if I apply it to that integrand, it will allow me to get rid of this division of an x term. So let's have a look. So here we're going to, and as I said, don't concern yourself or consider yourself lesser in any way, shape or form if you sort of go, well, how did you know how to do that? Like, okay, yes, I can see that it works now that you've shown me, but I don't know what I can actually take from that. I'm in the exact same boat. This just requires a lot of practice, picking up on other people's methods where they've found different ways of working, and then looking at new integrals and going, okay, well, this sort of has this part and that part. Okay, let's see if I can combine that. And as I said, that's why it's called a trick and not a method, because you just need to figure out the trick. So you'll see here I've slightly transformed the integrand, and I've included this e to the negative tx term. Now, the beautiful thing about that is that if I differentiate this with respect to t, it's going to bring this x down. And the nice thing about that then is that if I bring the x down, it'll cancel out with this x, and then it'll leave us with an integral that will essentially just have this component that will also be a negative. And this integral is a convergent integral. So that is why it's very, very critical here that I've set t to be greater than 0. Because if t is greater than 0, we know that x is positive, and so if t is positive, then we know that t multiplied by x is always going to be positive, and so therefore over this integrand from 0 to infinity for x, that means that this is going to converge, and we can evaluate that integral. Now, if we look at our original integral, what we actually want to evaluate, this occurs when I of t is equal to 0. So if I substitute t is equal to 0 here, I get e to the 0. Anything raised to the power of 0 is obviously 1, so we just get sine of x over x. We also know too that if I take the limit as t goes to infinity here, remembering that x is positive, so this is a positive term, well, e to the negative infinity is just equal to 0. So at infinity, for this point here, this becomes 0, which means that the integrand becomes 0, anything multiplied by 0 is 0, which means that the integral then becomes 0 as well, and this will become important later on. Okay, so as I said, the reason why I chose this is because with differentiation, with respect to t in this case, I can bring the x down. So that's what I'm going to do here. Now, I should have mentioned this before. In order to actually use this function here, we actually have to appeal to something that is known as the dominator convergence theorem. Now, again, if this is your first sort of go at this, don't concern yourself with that too much at this point in time. That's something, as I said, that I'll go into detail with in a subsequent video. Another theorem, though, that we need in order to be able to differentiate this function is known as Leibniz's integral rule. And it holds, in this case, there are certain conditions that are required on the integrand and the integral. And in this case, it is upheld. As I said, this will be covered in subsequent videos if people would like to see that. But yes, if I want to take the derivative with respect to t, I'm taking the derivative of this function. But with Leibniz's integral rule, that allows me to take the integral under the derivative, my apologies, under the integral sign, and obviously by transforming it into the integrand it becomes a partial derivative. Now we're taking the derivative with respect to t, so all of this x stuff just comes out the front, and so now we're just taking the partial derivative of e to the negative xt with respect to t, which is just equal to, so we see here sine of x over x is just still there, negative x e to the negative xt. And so that means that this x cancels out with this x, and I can bring this negative out the front, which is what I've got here. And then I've got the integral from 0 to infinity of e to the negative tx sine of x. Now, evaluating this integral is very, very simple. I'm just going to use the general formula here. I'm assuming that this is something that people would be able to derive. If this is something where you would like to see a video that shows how this is done, let me know. Essentially, what you can do is just apply integration by parts twice in order to evaluate this. But in this case here, we see that a is equal to negative t and b is equal to 1. So that's what we've got in terms of our form. You'll notice that I've omitted the plus c, the integration constant. And the reason why I've omitted that is because we're going to be applying it in a definite sense. So it goes away. Okay, so therefore di dt, which is equal to this expression that we had before, is equal to, and as I said, all I'm doing is just subbing in the values here. This is the negative that was out the front here, e to the negative ax over a squared plus b squared times by a sine of x, sine of bx, this should be, I apologize, there's a mistake here, this should be a b, so that's why we've got 1, minus b times by cos of bx, so 1 times 1x. So therefore, this just becomes e to the negative tx over t squared plus 1, t sine of x plus cos of x. So these, in case you're wondering, the negative here and the negative here gets cancelled out by this negative here, and the rest is just simplified. Anything multiplied by 1 is just that. Okay, cool. So now if I apply my limits, if I put infinity into here, remember, t is positive and x is positive, it's going to positive infinity. That means that this term is going to 0, which means that the upper limit is equal to 0. And then if I plug in 0 for the lower limit, e to the negative 0 is just 1. So I have 1 over t squared plus 1. T times by sine of 0, remember sine of 0 is 0, plus cos of 0, which is 1. So I'm just going to have negative 1 over t squared plus 1, which is what I have here. Okay, so that's what I was talking about when I was saying before. By changing the integrand and applying an operator, i.e. in this case differentiation, we then evaluate the integral under this transformation, and we get a result. So this isn't the result for I of t, obviously. This is the result for di dt, but we can very easily integrate this to get I of t, and that's the beauty of Feynman's trick. So that's what we're going to do. So di dt is equal to negative 1 over t squared plus 1, which means I of t is just equal to the indefinite integral of that. I'm assuming that people know how to do this. This is a very simple integral to do. If you would like to see a video on how to evaluate this, please let me know and I will do that. But basically, if you're unsure, just let t equal tan theta, and this comes out very easily. Anyway, the result becomes negative arc tan of t plus c, where c is the constant of integration, which is what we have here. So what we need to do is we need to evaluate what this integration constant is, and that's where this condition becomes important. Okay, so we know that I of infinity, or the limit of I of t as it goes to infinity, is equal to 0. We established that before. So that's equal to negative arctan of infinity, or the limit of arctan of t as it goes to infinity plus c. Well, arctan of infinity is just equal to pi over 2, so we have negative pi over 2 minus c. And remember, this expression is equal to 0. So if I just plus this onto, oh sorry, my apologies, there's another error within this. This should be a plus c. And so that would mean that if I want to resolve this, I have negative pi over 2 plus c is equal to 0, and that means that c is equal to pi over 2. So now we've established that this unknown parameter here, our integration constant, is equal to pi over 2. Remember, this should be a plus. I've made a mistake there. And so remember, we have 0 is equal to negative pi over 2 plus c, which means that c is equal to pi over 2. Okay, so therefore, we now know that I of t is equal to negative arctan of t plus pi over 2. Now that's fantastic. We've now not only got the result, or we have now got it into the form that we can evaluate our result, but we've even gone further. So we haven't just limited ourselves to the integral of sine of x over x, we've now extended it to include e to the negative tx as well. So by using this trick of making it more complicated, we end up also being able to resolve a far more complicated integrand. And in fact, actually, people may see this and go, "Whoa, this actually looks very similar to something that I'm used to," and that looks a lot like a Laplace transform, so you might want to have a look at that. Anyway, we know, as we had before, that j, our original integral that we want to resolve, is evaluated when I is evaluated at 0. So we have j, which equals I of 0, is equal to negative arctan of 0 plus pi over 2, that's our function here. Arctan of 0 is just equal to 0, so therefore negative 0, which is 0, plus pi over 2 is equal to pi over 2. And so therefore we have that the integral that we wanted to resolve at the beginning, j, the integral from 0 to infinity of sine of x over x dx is equal to pi over 2. Okay, great. So that's our first method. I'm going to do a follow-up video that I will be releasing very soon that actually evaluates this using the exact same idea. However, instead of actually needing to include a new term within the integrand, we can actually just modify one element of the integrand. So anyway, I hope you've enjoyed this video. If you have, if you could please put a like on the video. If you like these sorts of videos, please subscribe. And as I say in all of my other videos, I take requests and suggestions. So if you have an integrand or an integral or a family of integrals that you would like to see explored, please either leave a comment or send me a direct message. And if I'm able to, and I've got time, I will certainly put a video together for you. Otherwise, have a great day. Thank you. Bye.